Welcome back, everyone. In this lecture, we're going to focus on evaluating our model that we just trained in the previous lecture. Let's head to our Jupyter Notebook and continue where we left off. Okay, here we are at the notebook where we left off last time. After training the model, as always, what we can do is we can say losses, or actually in this case, we're going to say metrics is equal to pd.dataframe and say model history.history. And the reason I'm saying metrics instead of just losses is because let's take a look at what the history.history attribute actually returned. Because I also said keep track of accuracy here, not just loss, I get both my loss and accuracy on the training set, as well as my validation loss and validation accuracy, which means I can plot both of them out. So instead of saying metrics.plot, it doesn't make sense to plot both loss and accuracy, otherwise you'll get a plot that looks like this. Instead, you should be plotting loss versus validation loss and accuracy with validation accuracy. So what we'll do is we'll pass in a list here with loss and validation loss. Go ahead and plot those out. And we can see how the loss for the training set's going down, but it looks like the validation loss was essentially starting to go up again. So that's where we stopped the epoch training. And if we want to, we can also see the accuracy change. So we can see accuracy versus the validation accuracy. Note that the validation metrics basically just have VAL underscore added before them. And here we can see our accuracy continue on the training set, so that's good, almost reaching 100% accuracy, but our validation set started to level off when we ended training. Okay, so in case you want to remember what metrics are available to you in your model, you can say model metrics names, and it will report back the actual metrics there, loss and accuracy. And if you actually want to get the metrics of these, loss or accuracy, on any set of data, we can say model.evaluate, and we can pass in x test and y categorical test. Go ahead and say verbose is equal to 0 so you don't see the actual running of this data through the model. And it will evaluate and basically return back loss and accuracy on the test set. And it makes sense that these are 0.04 and 0.98 because if we take a look back at this, the last validation loss run on the test set was 0.04 and 0.98. So these should be essentially the exact same numbers as the very last loop or last epoch. And that's the evaluation on this test set. You could also do the same thing for the training set and it will report back these numbers, loss and accuracy. Okay, recall that accuracy is just a calculation of what percentages you get right. Loss here is the result of this categorical cross entropy function. Now that we understand how it performed during the epoch training, let's go ahead and just get the classification report and confusion matrix on our test data. We can do this from sklearn.metrics, import classification report, and we can also import the confusion matrix. So we run that. We'll go ahead and grab our predictions off of our test set. And for this case, we want to predict classes based off the information in the xtest dataset. And now we have our predictions. What we can do is recall that ycat test is still in the shape of 10,000 by 10. So what we want to do is make sure that we're comparing this correctly to ytest, which is these actual labels. So for our actual evaluation, we need to pass in ytest, no longer these categorical ones. So we'll say print classification report, compare the true ytest values to our predicted values, and we can see the classification report, essentially showing you the precision, recall, and F1 score per class. So how well did it do on zeros, ones, etc. And you can see it does fairly well across almost all classes with 99% accuracy. And if you want to do a deeper dive on this, you can do a confusion matrix based off that same data, ytest versus predictions, and you can see the results here. If you want to visualize this, you can also use Seaborn to transform this. So we can say Seaborn as SNS and then call a heat map, which would essentially color the results that we have here. So you can grab this and then paste in the results, and we can make this figure a little larger. We can say something like fig size equals 10 by 6. And you can run that and it will show you a heat map. Just need to add in annotations equal to true so I can see those values on top of it. So that's a way you can quickly visualize it. Not super informative here because of how well the performance is across all the numbers. Okay, so that's one way to visualize it. The last thing we're going to cover is how do you predict a single image. So if someone gave you an image of a single number, so for example, we'll say my number is equal to x test 0. So if I just plt imshow my number here, whoops, make sure I did this correctly, we'll say my number reshaped to 28 by 28. There we go. So here's my number. It's reshaped to 28 by 28, so I can visualize it. Clearly, it's a 7. So if somebody gave you this single my number, how would you actually predict it? Well, you would say model predict classes, and then the only thing you'd have to be aware of is this reshaping. So we would say my number dot reshape, and then the shape should end up being the batch size, so essentially the number of images, the width, the height, and then the color channels. So in our case, it's a single image, so that's 1. It's 28 by 28, and then there's 1 color channel. So that's why I need to reshape it that way, because that's the shape it was trained on, given the fact that we're feeding multiple numbers at a time. We'll go ahead and predict the classes here, and then when we get back, it predicts that it's a 7, which makes sense because here I can see it's clearly a 7. Okay, so the convolutional neural network performed very well on the MNIST dataset. Now that we know how to work with grayscale images, what we're going to do is expand our knowledge, and in the next series of lectures, we'll follow a very similar path, but working on color data with 3 color channels, red, green, and blue. I'll see you there.